Hello students, welcome to another video of F.Y.B.Sc calculus. Today we will discuss some examples of supremum infimum and after that the completeness property. So the first example is find the supremum and infimum. Find the supremum and infimum of the following sets. First set is, suppose set S is equals to 1 minus 1 upon n, such that before that we will take one set. Suppose first set is set S is equals to set of 1, 2, 3, 4 and 5. These all are natural numbers. So, to find the supremum and infimum of this set, we have to find the supremum, we have to find the least upper bound. Supremum means least upper bound. So, this set is bounded above because there exists the natural number, suppose 6, 7, 8, 9, 10. So, all the elements of set S are less than or equals to suppose 6, again less than or equals to 7. So, we have to find the least among all the upper bounds. So, here clearly 5 is the upper bound which is least among all the remaining upper bounds. So, the supremum is 5 and similarly infimum is 1, because the smallest supremum means least upper bound. Supremum means least upper bound, and here we can clearly say that 6 is upper bound, 7 is upper bound, 5 is upper bound, 6 is also upper bound, 7 is also upper bound, 8 is also upper bound, but the smallest among all those upper bounds is 5. So, this supremum will become 5, and similarly the infimum means greatest lower bound, greatest among all the lower bounds, So, here 0 is lower bound, then minus 1 is also lower bound, because all the lower bound means all the elements of this set are greater than or equal to that V. So, if you take V is equals to 1, so 1 is lower bound, because all the remaining elements, that is all the elements of this set S are either greater than or equals to 1. So, 1 is lower bound. Similarly, if you take V is equals to 0, then all the elements of this set S are greater than or equals to 0. So, we have to find the greatest among all the lower bounds. So, 0 is lower bound, minus 1 is lower bound, 1 is also lower bound. So, 1 is greatest among all the lower bounds. So, 1 will be our infimum. Similarly, if we take the second example as, suppose set S is equals to minus 1, minus 3, minus 5, minus 7. Then we have to find the supremum and infimum. Supremum means again least upper bound. Now, here first of all we will see the greatest number in this set. So, minus 1, minus 3, minus 5 and minus 7. So, this minus 1 is greatest number, this is the larger number. So, minus 3 is less than minus 1, minus 5 is also less than minus 3, minus 1, similarly minus 7 is the least number among all these 4 numbers. Now, this we have to find the supremum, we have to find the least among all the upper bounds. So, here if you take U is equals to 0, 0 will be our upper bound. Again, if you take U is equals to 1, then 1 is upper bound, because all the elements of this set are less than or equals to 0. Similarly, all these elements of this set are less than or equals to 1, but similarly all the elements of this set S are less than or equals to minus 1. So, if we take minus 1, then all the elements, here minus 1 is less than or equals to, minus 1 is equals to minus 1, again minus 3 is less than minus 1, minus 5 is less than minus 1, minus 7 is also less than minus 1. So, this minus 1 is lower bound. sorry, this minus 1 is upper bound, and this is the smallest among all the upper bounds. So minus 1 will become our supremum. Now similarly we will find the infimum, which is greatest lower bound. Greatest lower bound, and the greatest lower bound means the smallest element. We have first of all we will find the lower bound. Lower bound means the, suppose V is said to be lower bound if all the elements of this set are greater than or equal to that V. So minus 7, minus 8, minus 9, minus 10, all these are lower bounds, and greatest among all the lower bounds is minus 7. Since if we take these numbers on real line, this is suppose 0, this will become our minus 1, this is minus 2, minus 3, minus 4, this is minus 5, minus 6, minus 7, minus 8. One thing must be clear, that the elements on left hand side, are lower numbers as compared to the right hand side. So if we take suppose minus 4, then the elements, the numbers, the real numbers on right hand side of minus 4 are greater than minus 4, and on the left hand side are less than minus 4. So here minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. So minus 8 is smaller number as compared to minus 1. Similarly minus 7 is smallest, minus 6 is smaller than minus 1. So these numbers are minus 3, minus 5, minus 7 are less than minus 1. To find the least upper bound, we will find first of all the upper bound, set of all upper bounds. Number u is said to be upper bound whenever all the elements of this set are less than or equals to that number. So if we take u is equals to 0, then all the numbers, this minus 1, minus 3, minus 5 and minus 7 are less than 0. So this 0 will be our upper bound. If we take 1, then this minus 1, minus 3, minus 5 and minus 7 again less than 1. So 1 is again our upper bound, but we have to find the least among all the upper bounds, least upper bound, that is supremum, means least smallest among all the upper bounds. So here all the numbers of this set yes are minus 1, minus 3, minus 5 and minus 7, and these numbers are less than or equals to minus 1. Minus 1 is equals to minus 1, minus 3 is less than minus 1, minus 5 is less than minus 1, minus 7 is also less than minus 1. So minus 1 is also upper bound, 0 is also upper bound, 1 is also upper bound, but we have to find the smallest among all the upper bounds. So minus 1 will become our smallest among all the upper bounds. So minus 1 is our supremum. Similarly, to find the infimum, we will find the numbers such that we will find number V such that all the elements of set S are greater than that V. If we take suppose V is equals to minus 8, then minus 7 is greater than minus 8 because minus 7 is on right hand side of minus 8. So minus 7 is greater than minus 8. Similarly minus 5 is greater than minus 8, minus 3 is also greater than minus 8, minus 1 is also greater than minus 8. If we take suppose V is equals to minus 7, then minus 7 is equals to minus 7. We have to find the number V such that all the elements of this set S are either greater than or equals to. So minus 7 is equals to minus 7, minus 5 is greater than minus 7, minus 3 is also greater than, minus 1 is also greater than. So we have this minus 7 is also lower bound, minus 8 is also lower bound, minus 9 is also lower bound, and we have to find the greatest among all the lower bounds. So minus 7 is greatest among all the lower bounds. So minus 7 will become our infimum. So the supremum and infimum of these sets are minus 1 and minus 7 respectively. Now we will move on our main example. Suppose set S is given in the form 1 minus 1 by n such that n is the set of natural numbers. N is the set of natural numbers. Now we have to find the supremum and infimum. To find the supremum and infimum of such a sets, first of all we will try to write that this set in numerical manner. That is, if we put here, we have given that 1 minus 1 by n, and n is the set of natural numbers. So we can run this n from 1 to infinity. N natural number starts from 1. So if we put n is equals to 1, then this number becomes 1 minus 1 by n. Now if we put n is equals to 2, then we get 1 minus 1 by 2. If we put n is equals to 3, then we get 1 minus 1 by 3. Similarly, if we run this n from up to infinity, then if we put n is equals to infinity, then we will get 1 minus 1 upon infinity, 1 minus 1 upon infinity. So this set will be 1 minus 1 is 0, then 1 minus 1 by 2, 1 minus 1 by 2 is 1 by 2, then 1 minus 1 by 3 is 3 minus 1, that is 2 by 3. So if we run this n from up to infinity, then we get 1 minus 1 upon infinity, 1 upon infinity is 0, 1 minus 0 is 1. So the elements of this set are in between 0 to 1. So this is the smallest element of this set. So this is our infimum and this one is supremum. So supremum of this set S is 1 and infimum of this set is 0, because all the again if we take, suppose v is equals to minus 1, then minus 1 will become the lower bound of this set, but 0 is the greatest among all the lower bounds. And if we similarly here we can take 1.5 is also upper bound, 2 is also upper bound, but least among all the upper bounds is 1. So supremum is 1 and infimum is 0. Now the next example is, suppose same example, S is equals to suppose 2 plus 1 by n, 2 plus 1 by n, such that n is the set of natural numbers. Similarly, we can find this set 2 plus 1 upon n, n is equals to suppose 1. So 1, 2 plus 1 by 2, 2 plus 1 by 3, up to we can run this summation up to 2 plus 1 by infinity. N is the set of natural numbers and this set is infinite set. So we get this 2 plus 1 is 3, 2 plus 1 by 2, 2 plus 1 by 2 means 5 by 2, that is 2.5, then 2 plus 1 by 3 is 7 by 3, up to if we run this 2 plus 1 upon infinity, 1 upon infinity is 0, so 2 plus 0 is 2. Sorry. So we can see 3 is the largest element of this set and 2 is the smallest. So all the numbers of this set S are is in between 2 to 3. So 2 will be the infimum and 3 will be supremum. So supremum is equals to 3 and infimum is equals to 2. Supremum of set S is 3 and infimum of this set S is 2. Now the another example we will take is fifth example. Suppose this set S is given as 1 upon n, such that n is the set of, n is in between, n belongs to natural numbers. So we can run this set. If we put n is equals to 1, then we get 1 by 1 is 1. If we put n is equals to 2, then we get 1 by 2, then 1 by 3, up to if we put 1 upon infinity. So 1 upon n is equals to infinity, 1 upon infinity is 0. Similarly, we can say that the elements of this set are in between 0 to 1. So supremum will become 1 and infimum of S will become 0. So hence these are the examples of supremum and infimum. Now we will see the completeness property of R. The next topic is the completeness property of R. Completeness property of R. So in this topic, up to this lecture, we have seen the definition of lower bound, upper bound, greatest lower bound and least upper bound. Now we will see the completeness property. The first property is every non-empty subset of R which is bounded above has supremum and the non-empty subset of R which is bounded below has infimum. These are the two properties. So first property is every non-empty subset of real numbers, every non-empty subset of real numbers that has an upper bound, that has an upper bound also has a supremum, in R. every subset of R which is bounded above, that is the subset of R which has upper bound has least upper bound, that is this has supremum. And the second property is every non-empty subset, every non-empty subset of real numbers that has a lower bound also has an infimum, also has an infimum in R, that is every subset of every non-empty subset of real numbers which is bounded below has infimum. Now these are the completeness property. If we get the subset of R which is bounded above, then that set has supremum, and after that if we get the subset of R which is bounded below, then that set must have an infimum. This is the completeness property of R. Now we will see the Archimedean property of R. The next topic is Archimedean property of R. Archimedean property of R. This is the important property, Archimedean property of R. So to start the Archimedean property, before that we will take one subtopic which is useful in this Archimedean property, inductive property of N. Inductive property of N. N is the set of natural numbers, that is the property is if N is natural number, if N belongs to N, then N plus 1 is also natural number, N plus 1 is also natural number. N is natural number, then N plus 1 is also natural number. This is the inductive property. If we get N is equal suppose 10, then 10 is natural number, then 10 plus 1 11 is also natural number. This is the inductive property. Now we will move on the set. So again we will take one subtopic, well ordering principle of N. Well ordering principle or well ordering property, well ordering property of natural numbers. If S is subset of natural numbers, that is S is non-empty subset of natural numbers, then every non-empty subset of natural numbers S has least element. This S has a least element, every non-empty subset of natural numbers has least element. This is the well ordered principle. If you take any subset of natural number, then that subset has least element, that is there is a one element in that set such that all the remaining elements are greater than or equals to that set S. Now we will see the theorem on which is Archimedean property. Theorem which is an Archimedean property. Now the statement of the theorem is, if x is greater than 0, that is x is a positive number, then for any real number y, that is for any y belongs to R, there exists a natural number n belongs to natural number such that n into x is strictly greater than y, If x is a positive real number, also we have given that for any real number y there exists a natural number n such that n into x is greater than y. This is the statement of Archimedean property. If x is positive real number, and then for any real number y, that is there is no condition on y is either positive real number or negative number or 0. If y is any real number, then there exists a natural number n. Natural number starts from 1, 2, 3, 4. There exists a natural number n such that nx is greater than y. Now, to prove this property, we will take two cases on y, that is, first of all we will take y is less than or equals to 0, and after that we will see for y greater than 0. Now, to prove this property, proof of above theorem. In this proof we will take two cases. First case is if y is less than or equals to 0. If y is equals to 0 or less than 0, then the statement is x greater than 0, also n is natural number. So, x is positive number, natural number is always positive number, that is n starts from 1, 2, 3, 4. So, n is positive number, x is positive number, so their multiplication is positive number, and y is less than or equals to 0. If y is equals to 0, then nx is clearly greater than 0, because n starts from 1, that is n is either 1, 2, 3, 4 or so on, and x is positive number, so their multiplication is positive. So, nx is positive, then clearly if y is equals to 0, then nx is greater than y. If y is equals to 0, then nx is greater than y, because x greater than 0 and n is natural number, so their multiplication is positive. So, nx greater than 0 if y is equals to 0. Now, if you take y is less than 0, y less than 0 means y is negative number, and we know that the multiplication of two positive numbers is positive. So, nx is positive, and positive number is obviously greater than negative number. So, if we take the first case y less equals 0, then our result is obviously true. Then the theorem is obvious. Then the theorem is obvious. Theorem is obvious. Therefore, that is nx is greater than y for all n belongs to natural numbers. This is for y is less than or equals to 0. Now, the case second, for the case second, we will see whenever our y is positive. If our y greater than 0, then we have to prove that nx is greater than y. Now, we will prove this result by contradiction. On contrary, or in the second case we have taken y greater than 0, we have to prove that, that is our claim is nx is greater than y. This is we have to prove nx greater than y. On contrary, we will suppose this nx, we have to prove that nx is strictly greater than y. So, contrary, we will suppose nx is less than or equals to y. This nx is less than or equals to y. Contrary, we suppose the opposite result, that is nx we have to prove nx greater than y. On contrary, we will suppose nx is less than or equals to y for all n belongs to set of natural numbers. Now, we will consider the set. Now, therefore, consider the set yes, such set of this nx, such set of this all nx, n is natural number. If we consider this set, consider the set S is equals to this. So, clearly this set is non-empty, this set is non-empty, and also this set is bounded above by y, is non-empty set, and this is bounded above by y, that is there is a real number y such that all the elements of this set are less than or equals to y. So, this is bounded above by y. Reason behind this is nx is less than or equals to y for all n belongs to natural number. So, here we get nx is non-empty subset of real number such that which is bounded above. This set S is non-empty as well as bounded above. Therefore, by completeness property of R, by completeness property of R, by completeness property of R. Completeness property says that every non-empty subset of R which is bounded above has supremum. By completeness property of R, this set S has supremum. this set S has supremum, and suppose that this supremum is U. Suppose say that supremum is U. Therefore, if we take U is supremum, then all the elements of this set S, which is of the form Nx, are less than or equals to U, because U is supremum, less than or equals to U for all n belongs to natural numbers. For all n belongs to natural numbers. Now, here we get Nx is less than or equals to U. U is least upper bound or supremum. Therefore, by inductive property, here Nx is less than or equals to U for all n belongs to natural numbers. Therefore, by inductive property of n, inductive property of n means if n is natural number, then n plus 1 is natural number. So, if we put n plus 1 is also natural number, so n plus 1 into x must be less than or equals to U. So, if we put n plus 1 here, n plus 1 into x is less than or equals to U for all n belongs to set of natural numbers. Now, this will give us Nx plus x is less than or equals to U. This implies that this Nx is less than or equals to U minus some x, U minus x for all n belongs to natural numbers, for all n belongs to set of natural numbers. So, here Nx is less equal U minus x implies that this U minus x is supremum. N, all the elements of this set are, all the elements of this set S are of the form Nx, and this Nx are, all the Nx are less than or equals to U minus x, but U is our supremum. This S as supremum U, U is supremum, and we get the number U minus x, that is the number less than U, which satisfies the definition of supremum. This implies U minus x is upper bound. This implies this U minus x is an upper bound of S. But this is not possible because U is least upper bound. U is the smallest among all the upper bounds. Here U minus x is less than U, and this is also upper bound. This is not possible. But this U minus x is less than U, which is contradiction to U is supremum, is contradiction to U is supremum. So, here our assumption is wrong, that is this assumption Nx is less than or equals to y is wrong. Therefore, our assumption must be Nx greater than y. Therefore, Nx greater than y for all say they n belongs to where n belongs to natural number. Hence, the proof of Archimedean property.